Hi again everyone, Chris Tisdell here again. In this presentation, I'm going to continue my series of videos on complex numbers. Now, in this particular presentation, we're going to talk about regions or sets in the complex plane. So we'll talk about a few examples and a few different regions, and then I'll do an example. Okay, so let me share my screen with you and we can get underway. Okay, so just to refresh your memory, the complex plane, or sometimes called an Argand diagram, has a horizontal axis that is known as the real axis, and it also has an imaginary axis. So you have real numbers down here, say 1, 2, 3, -1, -2, -3, and on the vertical axis you have I, 2i, 3i, -i, -2i, etc., where I is the imaginary unit, right? I squared equals -1. Okay, so we're going to use inequalities to represent, say, two-dimensional regions in this complex plane, and essentially we're going to use lengths and angles. Okay, so let's just do a couple of real basic examples. So for a complex number z, we talk about the modulus of z, right? So if z equals x plus yi, where x and y are real, the modulus is just the square root of the sum of the squares of the real part x and the imaginary part y. Okay, now geometrically, if you have, say, a point lying in the complex plane, then the modulus is just the length of the line segment from the origin to the point. Okay, now let's consider the following set. It means the set of all complex numbers whose modulus is strictly less than 3. Okay, now this will be basically all those numbers or all those points lying in the complex plane whose distance to the origin is less than 3 units. Okay, so if I go out 3 units in any direction from the up to 3 units in any direction, I want to get all those points. So that will be a disk that's centered at the origin and is open and has radius 3. So let me just sort of draw in a little disk. Okay, so this will be 3i, and the reason I've drawn a dotted sort of edge is because we're not including the actual circle or the boundary of that disk, because you've got a less than. Okay, if we were to include the boundary or the circle, we would have to have a less than or equals to sign there. Okay, so this set is all those points lying in this open disk with center at the origin and radius 3, but not including the circle that bounds the set. Okay, all right, now let's look at a similar set. Here we've just changed something here. Instead of having this modulus of z, we've got the modulus of z minus some other complex number. Okay, 2 minus I. Okay, so what does that mean? Well, that's basically working off this and distance to the origin. Here we're now talking about distance to 2 plus I. Okay, so yes, so this now is all those sets of points, or all those points whose distance to 2 plus I is strictly less than 3. again, that'll be an open disk, but just with a different center. Same radius, but just with a different center. So let me see if I can draw that in. Okay. And the center now is at 2 plus I. So that'll be one of the axes. And the other one will be down here. Okay. Okay, so that's 2, and that's, I know it's very small, that's I. Okay, so radius again is 3. Okay, so again, I'm not including the edge because we've got a strictly less than sign there. Okay. So basically, to get from here to here, all we've done is kept the same set and just moved it. We've moved it so the origin has gone from the center has gone from the origin to 2 plus I. Okay. All right. So there's a couple of examples. Now, what about this one? Okay. Well, we've got an equal sign now, and we've got the modulus of z minus I equals 3. That's a set of all complex numbers whose distance to I is exactly 3 units. Okay, so what's that? That's the circle centered at I with radius equal to 3. Okay, so let me see if I can draw that in. So now we've got equals to, so we definitely want to, we're just including the boundary here. And we want to be something like this. And the center is at I. So that might be your I there. Okay, so I'm just interested in that circle. Okay. All right, well, what about this one? This one's a little bit harder now. This is the set of all complex numbers whose distance to 2 and distance to 4 are equal. Okay, so that's not quite that's a little bit strange on first viewing. And the claim is this is a vertical line passing through 3. So where does that come from? Well, let me just spend a little bit more time on that, and I'll actually just have a go down the bottom. Okay, I'll come back to this in a minute. Let's actually expand this and convince ourselves that this really is the right set here, or the right curve. Okay, so if I square both sides of this equation, I'll still get equality, right? So basically, let's start with this. We've got, so z is x plus iy. So z minus 2 will be x minus 2 plus iy equals x plus iy minus 4, which is x minus 4 plus iy, or yi. So if I square both sides, right, and using the properties of the modulus, basically it's this squared plus y squared equals x minus 4 squared plus y squared. Okay, so there I'm squaring both sides. So you know, I can put that in there if you like. Okay, so you can see straight away that the y squareds are going to cancel. And when I expand this out, the x squareds are going to cancel. So I'm going to get something like x squared minus 4x plus 4 equals x squared minus 8x plus 16. So the x squareds are going to cancel. You're going to get 4x equals 12. So x equals 3. So that'll be your vertical line, right? Okay. So they're the set of points that we're interested in for this one. Now, you can also involve angles in determining or forming or describing regions in the complex plane. Okay, so here we want all those complex numbers whose principal argument is between 0 and pi on 2. So if I just draw in my axes, then what is this saying? Remember, the principal argument is just the angle associated with the complex number and to the positive real axis. And the principal argument in this series of videos is always between negative pi and pi. So we start here, we're at 0. We want to go through to pi on 2. That's a quarter of a turn or quarter of a revolution. We want to include the situation where the angle is 0 and pi on 2. So this would be your region. It's essentially the first quadrant, including the positive real axis and I guess the top half of the imaginary axis. So there are a whole bunch of different sets and the inequalities associated with them. But let's do a problem. Yeah. So here we're asked to determine and sketch the set of points in the complex plane satisfying this. Okay, so just to recap, right? For z equal x plus yi, we have the modulus is this. And so the square of the modulus, let me just see if I can fix the focus on this for a second. Okay, there we go. And so the square of the modulus is just x squared plus y squared. Okay, we'll use all of those in a minute. Okay, so we want to get the set of points Z that satisfy this equality. So what does this actually mean? Well, we want the set of points whose distance to negative 4, because basically it's Z minus negative 4, is twice the distance to I. Okay, so the set of points whose distance to negative 4 is twice the distance to I. Okay, so let's write this out and see if we can do it. We're just going to do it algebraically. So if I square both sides, we're going to have the following. Okay, we're going to have Z minus negative 4 all squared equals 4 times Z minus I squared, right? So this is just, okay, well I can get rid of the two minus signs now if I want to. It's just going to be using this here. Z equals x plus yi, so Z plus 4 is going to be x plus 4 plus yi. So I take each of those and square them. And over here, I'm going to get 4. Okay, if z is x plus yi, z minus I is going to be x plus y bracket y minus 1 all times I. So it's x squared plus y minus 1 all squared. Okay, so now what I can do is expand these things and try to simplify. Okay, try to look for the equation of, say, a circle or something like that. Okay, that's what it looks like it's going to be. All right, so let's expand this left-hand side. So we're going to get x squared plus 8x plus 16 plus y squared equals 4 bracket x squared plus y squared minus 2y plus 1. And I can distribute the 4 in there, and I'll get something like this. All right, so let's bring the x squareds to the x's to the other side and bring all the constants to the other side. Okay, so I'm going to get a 3x squared over there. I'm going to get a negative 8x. The y squared will team up with that 4y squared to give me 3y squared. I've got negative 8y over there. And when I bring that 4 to the other side, I'll get 12. Okay, so this is going to be a circle. Okay, now what I'm going to do is try to simplify this and complete the square to put it in a suitable format. Okay, so I want to find the center of the circle and the radius. So first thing I'm going to do is divide by 3. Okay, because that'll give the coefficient of x squared 1, and it's easy to complete the square. Okay, so now I'm going to complete the square in x and complete the square in y. So complete the square. So I look at the coefficient of x and take half of that coefficient. Okay, half of negative 8 on 3 is 8 on 6, or 4 on 3. And then I add it, I square it, and I add it to both sides, and I do that twice because the coefficients are the same here. So I would get something like this. Actually, I'll take a new line. Okay, so I've added 2 things to this side, so I have to add those same things to the other side. Okay, so now I can simplify this just by taking the x there and what's in here, the y there and what's in here, and simplifying this right-hand side. Okay, so let me just move on to a new page. Okay, so over here, I'm going to get 16 on 9 times 2 will be 32 on 9. So 4 plus 32 on 9. That'll be 36 on 9, so it'll give me 68 on 9. Okay, so this now is a circle centered at 4 on 3 plus 4 on 3i. And with the radius, this will be the square of the radius. giving you this. Okay. Okay, so let's see if we can plot that. I'm going to do that in GeoGebra. So let me just share my screen with you and see if we can get that open. Okay. Okay, here we go. Okay, so let's go to the point, say 4 on 3 plus 4 on 3i. And then let's see if we can make a circle out of that. Okay. So let's choose that point and let's go for the radius now. So the radius is this. Okay. There we go. There is our. Let me make it a bit thicker. Okay, let's make it blue or something, and let's increase the thickness. Okay, so there you go. There is. Imagine this is the horizontal axis is the real axis. The vertical axis is the imaginary axis. Here it's labeled 1, 2, 3, 4. You know, in the complex plane, some people do, and I do it. I, 2i, 3i, 4i, negative I, etc. But in the GeoGebra, I haven't changed that. Okay, so there would be your setting and your circle. Okay, so that's my presentation. Hope you enjoyed it. A good way to get good at these complex region type questions is to do as many as you can. Try different things out. And in other videos, I'll be talking about more examples to give you some more insight into different situations and different contexts. So I hope you can join me for those presentations. If you have any comments, any questions, you can always post a comment in the comment section. Thanks for watching. Hope to see you soon. Bye.